Okay, good. I'm really happy to be here with you, and it's a very great opportunity for me to present these things and these techniques to you at this very intensive tutorial. Hello again, my name is Dmitry Ustalov. I'm the head of research at Toloka, and our research team is responsible for making the Toloka quality great and spreading our innovations made by the Toloka team, and especially the Toloka research team, to the world around us. And today I'll be focused on the second responsibility. I will be telling you how to obtain these good quality labels and how to achieve a good quality annotation from Toloka, and actually with any other crowdsourcing platform, because mathematics is the same for any platform you see. Let me begin with the formulation of our task, which is data labeling with crowdsourcing. And when you perform data labeling with crowdsourcing, you perform overlap of your objects. You have one object, you pass this object to multiple performers who submit their judgments, their opinions on the label, on the preference, or something like that. And you need to answer a lot of questions, which is the pricing questions, the number of labels questions, and so on and so on and so forth. It's a lot of things to do, and you need to care about everything. And I recommend considering the crowdsourcing annotation problem as the trade-off between accuracy and cost. And you want to either choose the labels at maximum accuracy for a given budget, or you need to minimize the budget for the chosen level of accuracy. And in my part, which will be consist of 3 elements, I will show you how to do this. We have 3 elements, 3 components here. Aggregation, which is the most intensive part. The second part is incremental relabeling, and the last part is performance-based pricing. Aggregation. And right now you have already launched your annotation projects, and you will obtain the labels. But again, usually you obtain multiple labels per each object. And if you do so, you need to somehow come up with a strategy how to select the correct response submitted by the performers. And it's not obvious. The good way is not obvious, and the obvious way is very clear. You can just check the most frequent answer, and you can use this most frequent answer, which is called majority vote, as a strategy. But let me show you how it works in Toloka. In Toloka, you have this interface, which is called the pool page, and you have the download results button, and you have this menu that shows you the aggregation options. And today you will know and you will learn how to use these buttons and what these buttons actually mean. Let me discuss the multi-class labels again. And multi-classification task is the task when you have some object. In this case, there's a pair of query and the URL. And you have a set of possible answers from vital, which is super relevant, super important, super useful, to irrelevant or maybe some not displayed options. And you need to annotate using your crowdsourcing platform these pairs, and you need to aggregate the responses because multiple performers submitted labels. I will introduce some notation here. We'll consider the possible labels as categories like cat, dog, other. We'll consider objects using J notation, and we'll consider performers using W notation. So a performer W submits a label K to the object J. It's that simple. And you can consider this problem of aggregation of your crowdsourcing results as the problem of aggregation in the following way. Suppose that we observe noisy labels. For every performer, for every task, we obtain the response. And our goal, our ultimate goal, is to recover the true labels. So we have the noisy labels, and we want somehow to recover the true ones, which is the ZJ objects for every task indeed. And a very straightforward solution here is just to count the number of votes cast to each label and to consider the most frequent vote as the true one. And this approach is called majority vote, and it is extremely robust and it works extremely well. Let me show you this slide. Here is a very well-known paper by Joe et al. That compared different aggregation methods for categorical data on multiple data sets. And you'll see that the majority vote strategy, which is the obvious strategy of counting votes, is extremely robust. It works really well. However, sometimes it's suboptimal, and it's actually often suboptimal, and you want to extract the most from your data. And to do so, you want to use a smarter approach. You want to use the approach that takes into account more relationships of your data, because you have this world in which you have people who submit responses, and these responses are submitted to multiple objects, and you need somehow to take into account this information to increase the quality of your result. And this is what will be presented right now. In order to improve something, let's study its properties. And the majority vote strategy has two properties. The first one is all the performers are treated equally, which means that every performer is good or every performer is bad. It does not differentiate between them. Another property is all objects are treated equally, which means that all the tasks you have are equally difficult or equally simple. It does not just care for this. And to do something better, to apply smarter methods, we need to parameterize the expertise of performers and difficulties of objects. As soon as we introduce some numbers, we want to build relationships of these numbers. And for this, we have probabilistic models, probabilistic graphical models. And right now in the slide, you see the plate diagram of a latent label model, which reads as follows. You have your response from the performer W for task J. And our model with the parameters I described in the previous slide says that the label we receive from the performer is affected by the expertise of this performer, which makes sense because a good performer submits better labels. The difficulty of this task, because it again makes sense, more difficult tasks are more error prone, and vice versa, simpler tasks can be solved with a higher accuracy. And with what is really interesting here, we assume that the response we have obtained from the performer is affected by the true response. You see the streak, right? We see that we got these noisy annotations, and we built a model that says that the true label also affects the noise we got. And to make this model complete, we want to say that this true label is affected by the frequency this label can be found in the data set. And the ultimate goal here becomes the following. We want somehow to model these relationships, these objects, and we want to recover this plate, which is not observed, but it's definitely possible using Bayesian models. Let me show you this trick. As soon as we have invented this model, as soon as we have defined the objects, which are noisy labels, true labels, expertises, difficulties, and popularities, we want to use some mathematics. We want to use some matrices to explain the probabilities of obtaining the correct responses given these conditions. And that is called noisy label model, which is the matrix of labels. And it is nothing but the probability of observing this response given the fact that the correct response was this. And indeed, we need somehow to recover the true labels using this notation. To do so, in probabilistic models, there is a concept called generative models. And we are running a generative process in which we do the following things. First, we sample the true label Z for the task J from the distribution P, which is the multinomial distribution, which is very commonly used in probabilistic models. And then, as soon as we sample this ZJ variable, we sample the observed noisy label from this distribution that contains the true label. And based on this model, we can explain the likelihood of seeing these true labels given the annotated data we downloaded from the platform. That's the core idea. We assume that the labels we got from the performers are conditionally independent of everything else given the true labels, the difficulties, and the expertises. And we can rewrite our plate model, this diagram, into this likelihood function. That is simply the product of probabilities and, well, marginalizing over everything. And remember that our ultimate goal is to get these latent true labels. To do so, we can maximize the L function and we'll be fine, but it's not that convenient. To do so, there is an algorithm called EM algorithm. The EM algorithm says that we can optimize this function in 2 steps. The first step is called E step, that allows you to estimate the true labels, and the M step that allows you to re-estimate the other parameters like the popularities of labels, the difficulties of tasks, and expertises of the performers. And based on these 2 interchanging steps, you can suboptimally but reasonably optimize your function and recover the true labels. And this is a very high level description of this model because you need something more to make this working. But generally, you can solve this problem using either analytical solutions, like exact form of EM algorithm, or using gradient descent, which is a very high performance, but expensive, computationally expensive operation. Usually people are talking about special cases of latent label models. We will cover 3 very popular ones. And these models, these cases are different with respect to the form of relationships and type of parameters they cover. For example, we will start with the Dawid and Skene model. This model was invented back in the 70s when nobody even knew about crowdsourcing. There was no such a concept like crowdsourcing, but instead there was a concept like medical examinations. And this model said that you have doctors who examine the patients and they say some diagnosis, some labels about their illnesses, okay? And these doctors can be considered as the performers, and these patients can be considered as tasks, and these labels can be considered as well labels, and it can be directly applied to the crowdsourcing scenario. And this model is very simple, and it has only 2 kinds of parameters: the popularities of classes, the labels, and the metrics of expertises. Yeah, and it does not take into account the difficulty of tasks because, well, doctors are considered experts. And unfortunately, since this model was invented back in the 70s, there is an exact form of implementing this using EM algorithm. You can just carefully write down on your favorite programming language these formulas, and you will obtain the algorithm that aggregates your crowd responses. Let us look at these steps carefully. At the E step, you estimate the true label by just computing this expression, which is the probability of obtaining this label multiplied by the expertise of this performer who responded this label and so on. And the M step, you use the computed true labels to re-estimate the matrices and the popularities. Having running these steps for quite a long time, for several times, the algorithm is proven to be converged. Another algorithm which is well known, which is called GLAD, Generative Labels, a model of labels, abilities, and difficulties. And this model performs a very similar trick, but in a slightly different scenario. The first one is you see that the task difficulties are now taken into account. And these are scalar values. However, the performer abilities are not matrices anymore. They are scalars as well. And this model uses slightly different parameterization to express the quality and the probabilities of giving the correct response K given the true response is C. The exact formula is present here. And this model was designed specifically for crowdsourcing back in 2009. And to optimize this parameter, you need to define the function A, which is some fraction with the exponent. You have some priors, and you compute the E step just like this. But since the M step cannot be reliably computed in exact form, you need to use gradient descent to estimate the parameters. But the core idea is the same. You initialize, you run this E and M steps, and after a few steps, your algorithm converges and you obtain the aggregated data. And another method is called MMCE, MiniMax Conditional Entropy Model, that models everything with matrices, and the loss function to be optimized has a different form. However, the core concept is the same. You have matrices, you recover these matrices, and these matrices explain how proficient your performers are and how difficult your tasks are. Based on this, we can build the following table that shows how each model expresses the relationships and objects. So Dawid and Skene model takes into account the difference between categories, but it does not take into account differences between objects. However, it indeed parameterizes performers. And it has this number of parameters. Other models have different numbers of parameters. And comparing to majority vote, these models are more complex, which means that in order to get benefit from these models, you need to have a larger data set. If your data set is really small, majority vote will be fine. However, our experience shows that if your data set is big enough, maybe thousands of objects and maybe thousands of responses, these methods do make sense and they do greatly increase the quality of your result. So by running a slightly more computationally expensive method on the same data set, you get the better data, and this better data is more carefully investigated by the method. Also, as a benefit, you obtain the parameters of your crowdsourcing setup, the performer expertises and task difficulties that you can use for post-processing and other steps. If you have questions so far, I can answer them. You can use the chat or you can use your voice.
I think we don't have questions in the chat. Let's wait for.
Okay, let us wait for a few moments. Okay, so there are no questions so far. I can return to this part as the questions appear. Let us continue, and the next step is incremental relabeling, or we call it dynamic overlap. And this is the screenshot of Toloka. And when you set up your pools, you probably have chosen some overlap. Overlap is the number of performers, unique performers, who annotate each task. So overlap of 1 means that every task is performed by only one performer. Overlap of 5 means that every task is annotated by 5 different performers. But dynamic overlap is something special, and it's something really useful. And let's consider this problem. You want to obtain aggregated labels of a desired level of quality using fewer numbers of noisy labels. And the idea behind it is very simple. You want to investigate and to invest the effort of the crowd performers to those tasks that really require very careful consideration. And if the task is difficult, you want the crowd performers to focus more on it. If the task is simple, you want people just to make sure that the response has been submitted. So it allows you to balance the crowd effort between the difficulties of tasks. And this is a real-time algorithm that performs the following activities. For every received label, so you get some label for some object, you do the following real-time computation. You remember the previously accumulated labels and the new labels. And this algorithm uses probabilistic models to decide whether you should stop annotating this task or you need maybe one or more additional responses from the crowd performers until all the tasks are labeled. So until it gets some confidence, it will receive and demand more tasks, more responses. And the notation is very similar here. We consider one object. We know that there is some true label Z, and there is some observed noisy label Y. And again, suppose that we have already built the noisy label model for performer, and we can do this using some aggregation model like Dawid Skene or something like that. And using these models, we can compute the probability of getting the correct response K using the noisy labels we have, using this Bayesian rule. Just by simply recomputing these probabilities, we can obtain the probability of getting the confident response given the noisy labels we got. And how it works in practice. Suppose you have already defined this aggregation model, which is Dawid Skene or something like this, and we compute the expected accuracy of aggregated labels given the noisy labels we got. And we stop labeling if this expected accuracy exceeds some parameter C. Okay, we define some parameter, we compute this expression using Bayes rule, and if the probability of obtaining the confident confident true label is greater than C, you stop your annotation. And the core idea is you need to select this parameter. To do so, you want to build a graph called cost accuracy graph, in which you have the x-axis with the cost and the y-axis with the average aggregated accuracy, and put some points there. You need to perform some experiments. And once upon a time, you will see that at some threshold called C, in this example, it's 0.95, but your example, your mileage may vary. You'll see that the returns are diminishing. So your accuracy does not increase after paying more. And this allows you to set up this threshold and use it as the C in the previous form. And our experience shows that dynamic overlap saves about a third money that you spent on annotation by spending less on the simpler tasks and spending more on more difficult tasks. It's a very useful technique that is implemented in Toloka, but indeed you can do this on your own. Just use these equations to compute these expressions. And the last part for today, well, let me stop and ask you if you have any questions so far. Okay, no questions so far. Let's continue. Let me tell you about performance-based pricing, which is called dynamic pricing. And indeed, in Toloka, you need to set up the price you pay for the labels, but it makes sense to think that you need to pay more to those who handle your tasks better. If the person can handle your task better, you might want to pay more them. And to do so, let's continue and consider labeling as a game from a game theoretic way. You have a two-sided market. You have the performers, you have the requester. And the performers receive this task and they put some effort to obtain the accuracy, and the accurate labels make some value to the requester. And let's think that the requester payment is somehow dependent on the accuracy provided by the performer responses. And to formalize this, we consider this setup. Each performer W chooses the level of effort to maximize the earnings per unit of spent effort. So H is the effort, and you want to maximize this fraction. And at the same time, the requester chooses a pricing to minimize payments per unit of obtained value. So if we assume that the accuracy is linear to the effort, of the performers and requesters maximize their utility if the pricing is proportional to the accuracy. Simply saying, if the pricing is proportional to the accuracy, the game maximizes the utility. That's the idea. And the implementation is defined here. Suppose you have the price defined for the high level accuracy. So you need to somehow to define some A0 parameter, which is the high accuracy that you pay the full money. And you need to think about estimating the quality of the performers. And the basic way for doing this is to compute the fraction of correct labels per golden set, which means that you run the annotation and you compare a subset of the data submitted by the performers with some golden data, golden labels that can be predicted by you or maybe downloaded from somewhere. You compute this probability of providing the correct response. And you say, okay, this is the quality of our performer. And then you say, okay, this is called weighted majority vote. And the weighted majority vote means we do the same thing as in the majority vote strategy before, but instead of counting each vote in the same way, we weight them using the accuracy on these golden sets. This allows you to provide weighting and computing the weighted majority vote estimate. And the incremental relabeling and this dynamic pricing methods are based on this expected accuracy. And the core idea is the following. If your quality is the same or higher than the defined name value of quality, then you pay the full price. However, there is another option. If it's not higher or equal this defined level of quality, you need to find an N, which is the number of responses needed to dominate the majority vote, the weighted majority vote, using this level of quality submitted by the performer. And based on this, you pay inversely proportional to this value N. And that's the core idea of performance-based pricing in practice. So basically, you want to promote those who perform the task better, and you want to clearly explain that if the accuracy is not very good, you need to do some more training tasks, you need to do some better exams, you need to be careful with the instruction, and as a result, the payment will be better. And this concludes the third part. Thank you very much for your attention, and if you have questions, I'm really happy to answer them.